Looks like we're up and running. Get a full screen here so I can hopefully capture everything that I'm talking about. Sometimes I move the camera around and I realize that you're not seeing what I'm talking about. So it's about the product rule, and we'll be at that in about 30 seconds. I realized I probably should have done a video on quadratic change. I know I've done numerous ones on cubics. But the geometry, early geometry of squares and cubes is what I think has generated a lot of the calculus concepts that we're studying. So some helpful videos might be geometric view of integration and the relationship between differentiation and integration. I start my calculus classes day one with the relationship between differentiation and integration. Those are the two main concepts, and I want to talk about them the whole semester. So if you pause the video, you can look at how a square changes. It's really a layering process, and it involves the two side lengths of the square. It's got some numerical support. So for those of you studying calculus, y equals x squared, y prime is 2x. And at 3, y prime at x equals 3, we can see is 6. So on the quadratic, 3 gets you 9. And we're going up at 6 to 1, and you can look at that and pause the video. Now we're going to go after the product rule. Okay, so one of the most famous products, certainly length times width equals area. And I think it's probably our easiest product to look at is some situations like x plus 2 times x plus 4. Studied algebra 1, it's factorable. It's also easy to put this into graphing form, well, a little bit of practice. And if you're looking at the product rule, I'm assuming you already know what the derivative of this is, 2x plus 6, and we're going to dive into the numerics of the product, x plus 2 times x plus 4 as we move along. If we look at differentials, this kind of gives us a sense of the differentials. It's going to, that the differentials of length times width is the layering process of new area, making a slightly bigger rectangle and subtracting the two areas and dividing it by the change in the dimension gives us a feel for rates of change. So at 1, 2 times 1 plus 6, we get 8. And that's using your standard polynomial differentiation, which I'm again assuming if you're looking at the product rule, you've already done. Okay? But you may not know what you were doing. And so hopefully we can dive into that a little bit and maybe help some folks understand it at a little deeper level. So here's the product that gets us x squared plus 6x plus 8, x plus 2 times x plus 4. And I'm suggesting that a little change in the dimension here of this side of the triangle, and I can't show it. I mean, the kinds of change I'd like to show over here, 0.001. I'm just going to change this dimension when x is 1 by 0.001. So when this is 1, we have an area of 15. When I change the dimension by 0.001, it looks like I'm going to go back and forth a little bit here. Okay, 3.001 times 5.001 gets me 15.008.001. And if we look at the 3 decimal situation here, well, there's our 8 to 1. We can see it numerically here. If we take the time to do it out. All right. And so what I'm suggesting here is that if we change this by 0.001, well, we have a new rectangle. And its length is really 1 plus 4, 5. And so that would get us 0.005 of new area. And if we did that over here, well, then we got to use this dimension, which is 3 when I put 1 in, times 0.01 is 0.003. 0.003. And if I add those two things up, 0.005 plus 0.003, well, there's my 0.008 divided by 0.001. I guess I'm showing it here. There's your 8 to 1 units of change. And so what did we really do? Well, we changed the length. If this is L, then we can think of this as our dx, right? Our change in x times 5. And over here, change in x, right? A little difference in x, 0.001. And we can see that our change in y is coming from 5 dx in this instance and 3 dx. And if we divide by dx, we can factor dx out. Divide this, well, that's where we're coming up with a derivative. And at x equals 1, we're getting an 8-to-1 relationship. So I like to think of length times width. And let's see. So the product rule is take the derivative of the first function, multiply it times the second, plus the derivative of the second, multiply it times the first. So what's the derivative of x plus 2? What's the easiest situation I can think of? It's 1-to-1. All right, and so at 1 plus 2, the derivative of this is 1. And holding that constant, 1 plus 4. You can see here gets us 5. And then if we do the derivative of x plus 4, which is also 1, times x plus 2, we substitute 1, we get our 5 plus 3, which is 8. You can kind of see where, this product rule comes from. Now I'm going to do a more complicated one in a moment. But if we looked at it from the context of individual terms, the derivative of x squared is 2x. And I think if you see a slight change here and we square it, well, I think you can see that, we've got two sides of a rectangle, special case, and we're just adding up those two sides. Whatever those two lengths add up to, well, that's what we're going to get here. And 6 times 1 is 6, but 6 times 1.01 is 1.06 plus 8. And I added those up over here, those changes to 4 decimal place accuracy. Lo and behold, 8-to-1, 4 decimal place accuracy. I think 5 decimal place accuracy is going to get me 8-to-1. I think 6 decimal place accuracy is going to get me 8-to-1. I think we're talking about limits now, right? That we can push that error, which is really the cusp. What I'm really doing here is multiplying 0.001 times itself. And I can push that decimal out. Look how far out it went. So we can ignore it. And we know where we're trending towards. So what else did I want to show? Well, I just also wanted to, just from an Algebra 1 context, we always call this, we know it's a linear term. But at the same time, it's also part of a product, right? That part of a product which is giving us area accumulation. So even though it's a linear term in this context, it's generating area. I always found that a little interesting. Okay, and I was going to say something there, but I forgot. But you can also use this product rule to develop the quotient rule. I mean, dividing by 2 is the same as multiplying by 1/2. So we can apply area times 1 over width. It's going to get us length. And I think I'll do a video on that in a little while. But next, we're going to do the product rule, an approximation first. And then we're going to check it out with a calculator and see how close our approximation is. Come on, Cart, do what I'm asking you to do. All right, so here we are. I think I'm going to move the cards out of the way. Get that on the desk. All right, so I decided to look at the product y equals sine x times x squared. And the product rule says that y prime is cosine x. Take the derivative of the first function, multiply it times the second, plus the derivative of the second times the first. And I thought, wouldn't it be fun to just do a little approximation? So I decided to use x equals 3 again. Now radians is, a distance of 3 units around a circle with a radius of 1. Takes us almost 180 degrees. Right? And 3.14 approximation for pi right here. And I'm going to blow this up over here so we can look at some change. All right, so what's happening to the altitude, the sine function? The altitudes are coming down as I move in this direction. And the radians are going up. And it looks like it's almost 1-to-1. And if I draw one period of the sine function and zoom in at about 180 degrees, and I'm looking at here, you can see that the sine function is going down at 1-to-1. Okay. So let's throw some numbers in here. Let's approximate some numbers. And do I have that over here? Let's bye-bye cart, go that way. Let's do some approximations. And so I threw in the cosine of 3, which I think we can see the cosine of 3 is this distance and in a unit circle, you know. Yeah, I can't really show this, it's so small, right? So we're really close to pi, and the cosine of pi is -1, so that's our length, right? So this cosine of 3 is pretty close to this number. Not quite -1, but it should be pretty close. And if we square 3, we get 9. So I did -1 times 9. No, I'm not gonna try to throw -0.99 whatever to get a little closer. And the sine of 3, again, the sine of 3 is about the same as the arc length, right? This length here is very similar to the altitude. If we're looking at the sine of 3, then this y value is pretty close to the difference between these two. All right, so it's pretty close to 1.4. So I used it. And I said 6 times 0.14. I didn't need a calculator. I could do -9 plus 0.84, -8.16. Calculator told me it was -8.06. As far as I'm concerned, that's okay. Think I'm seeing what's going on. And the numerics support it. And hopefully the video may help some folks understand where the product rule comes from. All right. And then I'll do the quotient rule probably tomorrow. Okay. Have a good day, everybody.